conformal way to think about N3 as the boundary formula. And then the CR geometry means the following. So this time, we want X4 to be complex. So X4 theta. Then N3 is the boundary. Okay, so you want, again, N3 is given by a defining function rho, and then you want rho to be a pseudo-complex. So when that is the case, this well-known theorem of Schultz and Zhensao, Chen and Yao, said there exists a complete theta minus m. And then, well, the boundary now, instead of a conformal structure, now the boundary has what's called a CR structure. So now the boundary has a CR structure. So what does that mean? Well, intuitively, it just means that the Cauchy-Riemann equation still makes sense on the boundary. But more precisely, say in the following, right? Say, so now I'm thinking about N3. And then there's a contract form, so theta is going to be D conjugate with rho. So this is really the imaginary part of the So this is a contract form. And then I have a almost complex structure. So this is abstract CR manifold. So contract form means that d theta, wedge d theta, is never zero on all of the insertions. That's certainly the case if I'm looking at the situation. And then the kernel of theta is a two-plane distribution. So we want J to be the almost complex structure of the kernel. In other words, J squared should be minus the. So when you're given such a abstract CR manifold, you can always, given such a complex structure, you can always find such a J. So in a sense, the problem is that there are too many such J's. Okay. So what are the major questions? Say the major questions are the following. Right? So first, what's called the embedding problem. That is, given such a thing, how do you know there exists such an X? Given the X4. It's the question we try to answer. And then, of course, the other question is more general. That is, now you want to find enough local invariants. Right? So, find enough. Invariants to classify such a 3 node. Okay. So, try to talk about these questions today. So first, let me just say, this embedding problem, in higher dimensions, is completely solved. So we're looking at the lowest odd-dimensional amount. So when m plus 1, we have to come that form. Yes. This embedding problem is 1. basically the work of Ted. Remove that. And the reason is really the following. In their definition, they make an extra assumption that J is called integral. What does that mean? It means the following, right? So when you have an almost complex structure, the differential form can be split into 1, 0 type and 0, 1 type. So one form is decomposed into 1, 0 part plus 1, 0. So you have the round differential now split into E and E part. But since we're on the boundary, so we look at the projection to the compact part. Okay? So you have such a decomposition. And then to say integrable is that natural condition that D or P squared should be equal to 0. You know that D squared is 0, right? It may be 0 because of cancellation. So you insist in D bar. That is, say, D bar twice, you should get 0. This is the integrability condition. But in 3 dimension, this integrability condition is vectorless. So you don't have a local formulation of integrability. That's why the problem is interesting. But in higher dimensions, because of this natural condition you can impose, embedding problems is rather easy. Okay. The other part has to do with finding enough local invariants. So maybe I spent just a few minutes writing down. It should show you how you construct these local invariants. So this is pretty basic stuff. Okay, so to define local invariants, first let's normalize things a little bit. Okay, so first I find the following. I choose T, a vector field. V vector field. You can choose it in a canonical way, that is given to theta, you want the V derivative of theta in the T direction to be equal to 0. So if you give it to a calculus student, I'll bet you can figure it out. You can find such a unique T. Theta on T. So this normalizes T. The vector field T should be dual to theta. And then this extra side condition determines it uniquely. Then you want to choose framing, choose E1, and then E2 to be J of E1, maybe say basis for the compact distribution. Okay, so framing. And then you want, so this is arbitrary, but then if you require d theta to be exactly, so once you have chosen E1, E2, and T, then E upper 1, E upper 2, and theta be the dual. So once you've chosen these, the dual is fixed. And you want d theta to be exactly vector 1. Depending on the moment. Okay. So again, this is elementary. Given such a T now, theta, and then you can choose E1 and E2 so that this is set. So this determines. Okay, so after this normalization, now you want to introduce a connection. So this is called the Webster Banaka connection. So you want a connection so that the covariant derivative, well, see now since I have d theta is non-degenerate, right? So I can think about d theta acting on a pair of vectors as a metric. So I want this metric here. This to be parallel. other condition is that the torsion should be strong. So this is again an exercise in calculus. Okay? When given such a structure, then such a connection can be done. In 3 dimensions, the exercise of calculus. Higher dimension takes down the tricks. Okay, so this is easy. So then this determines what's called the Webster-Tanaka connection in this dimension. All right, so once you have a connection, you have curvature form and so on. Okay, so let me write down. So given this connection, and then here is curvature. Now the difference between this geometry and the Riemannian geometry is that this connection has torsion, just like the Hermitian geometry. This connection has torsion. So I will not write down the formula. So there's a curvature and there's a torsion. But in 3 dimensions, there's only a scale curvature function, the only curvature of the contact plane. So there's a curvature function that's called a Webster curvature, and a torsion that's called torsion is the tensor, so it's called. So these are the local invariants that completely determine the local geometry. So these invariants determine. So at this point, let me just introduce the basic example. What's called what we call the flat space. Heisenberg. So we basically are assuming x y t, and then we have theta is dt plus x dy, and x dy minus x. You can check that d theta is 2. So theta was d theta is exactly the number 0. So now you take the E1 vector field partial x plus y p E2 partial y equals y. Then you can check that this is a framing satisfying these conditions. And you can check that for this model, the Webster curvature is 0 and the torsion is 0. So this is what we call the flat model. Okay. So these are the local invariants. And then these questions sort of stood open for a long time. So we had the problem. Local invariance and global invariance. We'll try to prove some basic computation results. So the main idea really comes from conformal geometry. Okay. So what I'm going to do is I'm going to mention a few important facts about conformal geometry. And in fact, we think about conformal geometry in format. Format of dimensions. So the first important thing about conformal geometry in 4 dimensions is that there is this Yamabe equation. So in dimension 4, it looks like this. It's called L. It's minus or plus Riemannian function plus scalar curvature over 6. So it's a second order linear operator. It's 0 and the Yamabe operator has conformal properties, conformal covariance. That is, now if I make a change in metric, right? Say G tilde is what? U squared times G. Where U is a positive function, it's called a conformal change in metric. Then this metric G tilde has its own conformal Laplacian. And these two are related this way. So you apply it to a function B. It's the same as multiply E by U first, and you apply the conformal Laplacian associated to the G metric, and then U to the this conformal covariance. So now if you apply this to the function 1, yeah, apply this to the function 1, you get the scalar curvature. So you get the Yamabe curvature. That is, we're looking for a positive function U so that LU is equal to constant over 6. So the new scalar curvature is a constant. It's Yamabe. So this is the unity equation, semi-linear unity equation that's best studied. And many people in this room. Okay, so there's conformal geometry, and then, so the interesting thing is that in CR geometry, there's just the exact analog. Okay? So there's CR geometry. Now I'm looking at M3 and say that, okay. So we have an analog of, because now we have curvature, I think about that as the analog of the scalar curvature. So we still call it the CR Yamabe operator. And let's now change the contact form to say the tilde, and I use the same U squared thing. And then I have this CR conformal Laplacian. So I have this sub-Laplacian plus vector over 4. Unfortunately, it's 4. But you call it, you redefine it, so it's 6. Right. So I have the same conformal covariance. It's the same. Okay. So now, everybody knows that the Yamabe equation has been solved. Yeah, basically, work with many people, Oban, and Rick Shane, basically. So in CR geometry, there's the same question. In particular, in dimension 3, can you solve that? Does there exist a positive U so that this equation is solved? So this problem actually has been studied by many people. So the first one to study this in this dimension is actually our teacher, Chen and So they studied the case with the operator because of this conformal covariance property. So to say that with L tilde, this operator here, has a sign. In other words, it makes sense whether the operator L is positive or not. That is, look at it's an elliptic operator, so look at the lowest eigenvalue. So if the lowest eigenvalue is negative, we say that we're in the negative conformal class. If the lowest eigenvalue is 0, we say we're in the 0 class, flat class. And then if the lowest eigenvalue is positive, so L has a sign according to the lowest eigenvalue. So it turns out this problem is relatively easy with the lowest eigenvalue is non-positive, then there exists a solution. In fact, it's what's called minimizing solution. By minimizing, I mean the following. Okay, there is a variational functional for which this equation is the Euler equation. Okay, so the variation function is the following. You look at L of U times U, you integrate it over this manifold, and then divide it by the L4 norm squared. So because this is quadratic in U, it's homogeneous, so now you can look at the E. So you say that we have a minimizing solution, if that solution is a minimizer of this function. Okay. So Chern-Hamilton has this result. And then later, a student of Henri showed that, well, nevertheless, in this dimension, this thing always has a critical point. Exists. In other words, there exists a solution. Okay? It may not be a minimizing solution, but still a solution to this equation. But for geometers, of course, the interest is to find the lowest energy solution, because we want this constant. We want control of this constant. If the energy is high, this constant is high. Okay. So what I want to do is really talk about how to think about this problem. So it turns out that it's possible to solve this equation, but you have to bring extra operators. So let me continue this analogy now. Okay? So in addition, now there's this what we call the Penny's operator. So this column is the Riemannian case for the full member. So this P is basically the biharmonic operator plus second order term. So I forget what's the divergence latex is minus. So I form my number of the Riemannian exercise of each tensor to form my four matrix. I take a function, I take its derivative, I take its gradient, and then multiply its gradient by this four matrix, and then I take the matrix. Second. So this operator has many magical properties. The most important one is the conformal covariance. Now this time I write G tilde in the potential 2,000. Then, if I have a new metric, then I have a T tilde. Right? So T tilde applied to a function P turns out to be a solution minus T original T applied to the same function. Okay, so when in geometry, whenever this happens, this operator defines the curvature quantity. And now we call this curvature Q curvature, a generic name. So it defines Q curvature. So what's the Q curvature? Well, something like this. Q curvature is something like minus plus minus what we call sigma 2. So A is a multiplication of Ricci. So it's a Ricci So this is a symmetric 4x4 matrix, so it has eigenvalues. Right? It has 4 real eigenvalues, and so the symmetric function, second symmetric function, is 4 eigenvalues. Okay, so anyway, what's important about this is the following. The integration of Q has topological significance. So it turns out something like integration 12Q plus 12 times Q plus the Weyl tensor squared is 4 times squared times Euler number formula. So in fact, in my earlier work with Alice Chang and Matt Gursky, we used the positivity of these two operators to draw a lot of conclusions on this format. So it turns out that in CR geometry, there's an analog of this operator. So I think this operator, we call it the Dirac operator. Not because he invented, somebody else invented it but didn't know what to do with it, but Hirashi realized that this operator has the following importance. Okay, so this operator P is similar, it's a subplot square plus, now remember T, yeah? The T vector field, T squared, and then plus the lower order terms. I forget what the terms are. But the lower order terms involve proportion. Okay. And it has the same conformal covariance property. Right? Change the contact form to its theta. Then this also happens. Therefore, it defines the Q curvature quantity. And the Q curvature quantity is something like Q curvature is 3 over 2 over 3 minus sum of the scalar curvature, the Webster curvature, and then plus eventually plus figurative portion. Anyway, so what about Gauss domain? Well, it turns out, this is Hirashi's result now, integration of Q, say that he said, is always 0. So no information. Still, Q has other information. So let me just oops. Okay. So now remember, suppose my 3 manifold is the boundary of a, say, pseudo-convex domain. So if U3 is the boundary of a pseudo-convex manifold domain. Then that domain has L2 holomorphic functions. Huh? And L2 holomorphic functions have trace on the boundary. So I have the Seiko projection. Okay. So there's a Seiko projection. So this is an analysis, complex analysis of a pseudo-convex domain. And then the famous work of Feckerman and Petet says that the Seiko kernel has asymptotic expansion. So you take SPP and you look at the kernel on the diagonal. Okay? And then it's asymptotic to, well, let's see, I have the defining function rho, right? Defining function rho. Okay, so it's asymptotic to a constant over rho squared. Okay? And then plus maybe a log term, log rho, and then smooth part. Okay? But the coefficient in front of the log is this cube curvature. Okay? So this is a highly non-trivial thing now, right? This expansion, this is cube curvature. So those of us old enough, maybe not, one of you. So when Pfefferman studied this Bergman kernel, he wants to prove that biholomorphic maps continue smoothly to the boundary. Now, if the Seiko kernel has no log term on the boundary, then the smooth extension is rather easy. Okay, so a lot of work is spent trying to deal with the case with this coefficient here is non-vanishing. Okay, so this explains a little bit about what our operator, or the Irachi operator, has to do with the complex analysis of the manifold in question. All right. So now this operator here is not a elliptic operator, not even a subgroup. Because if you look at the energy term, E applied to U times U integrate, then you get the integrate by parts, so you get the sum of plus U squared. But then this one, when you take that part, you put a minus sign. So these two guys are fighting each other all the time. It's not elliptic. It's like a wave line. Okay. But the interesting thing here is the following. Okay? This is known to people before, this is the example. That is, the kernel of this Irachi's P is really contains the Fourier harmonic functions. That is the real part of holomorphic functions. So if you want to study holomorphic functions yet, you have to deal with the Fourier harmonic functions. In other words, you have to deal with this operator P. And P is a higher order operator. So this makes things difficult. But on the other hand, what we want to talk about is, well, in conformal geometry, when these two operators are positive, then many good things happen. So the same thing is happening here in CR geometry. Here now, we'll talk about this stuff. So this is the answer to this embedding problem. Okay? So this is joint work with Xu Hongling here, and then Safung Shanino. If I'm in this situation, I'm looking at a 3 manifold and 3 contact form, then I have this conformal Laplacian, I assume it's positive. That is, eventually we want to deal with this harmonic problem that is positive. So putting that assumption, and now you put in this assumption.